Okay, section 1.4, Numeral Systems. This is part of a book I wrote with Garbini and Devine. Check it out on the MIT Press website and rtcbook.org. Okay, numeral systems. To effectively understand memory representations, which is what we're doing right now, proficiency in numeral systems is essential. This section provides a review of positional numeral systems as preparation for section 1.5 on memory. Before diving into the technical details, we begin with a whimsical story to explore the motivation and requirements for representing numbers in positional numeral systems. The myth of Niles and Pepper. Two of my dogs, by the way. Niles was an unusual boy with great hair, living in a time before numeral systems. Quantities were familiar, but symbolic representations of them were not. Niles lived in a grove of trees. A grove on the other side of the hill was a home to his friend, Pepper, a sassy, no-nonsense girl. One day, Niles and Pepper were walking together and, as children do, began arguing about whose grove had more trees. If the argument had been about who had more skipping stones, they could have simply matched up stone for stone to discover who had more. But this was impractical with the trees. Niles had an insight. We could represent each tree by drawing and match them to determine who has more. So we can just match the drawing instead of the tree itself. It went something like this. Niles drew these trees, Pepper drew these trees, and we discovered that Pepper had more trees. Not to be discouraged, Niles proposed that instead they each compare the number of trees on their side of the hill. However, there were many more trees, so Pepper suggested that they simply draw the symbol T to represent each tree to save time. The results were no more satisfying to Niles. Here are all the T symbols representing the trees, and here are Pepper's representing the trees on her side of the hill. Niles pushed on. Let's include the neighboring hill on each side. With so many more trees, Pepper suggested a shorthand notation. We can compactly represent the number of trees with two symbols. I'll call them 0 and 1, used in combination. She explained it to Niles by tallying it up. So, for representing no trees, we'll use the 0, and for representing one tree, the line. 2 trees, a line and a 0. 3 trees, 2 lines. 4 trees, 1 line and 2 zeros. 1 and 2 zeros. 5, 1 0 1. 6 1 1 0. 7 1 1 1. Okay, that is, each position could take on 2 symbols, but the position of each symbol denoted its weight. The rightmost symbol represented either a lack, 0, or presence of a single tree. So the rightmost on all of these is the lack or presence of a single tree. The next symbol to the left was the overflow from the first symbol, and therefore represented the number of pairs of trees. So for instance, a 1 there, and the second to right, represents 1 pair of trees. The next symbol to the left was the next overflow, representing pairs of trees. So this third symbol to the left in this example represents a pair of pairs of trees. What fun! They started counting, and Pepper immediately recognized a process improvement. If we use more symbols, we can represent numbers even more compactly. Pepper suggested a symbol for each digit on their hands. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now they could count as follows. 0 through now 10 up here. We've got the overflow. We ran out 0 through 9, and then the overflow happens, and we have one group of 10. That is, the second symbol now represented a group of 10 of the group to the right. The rightmost, the number of trees. To its left, the number of tens of trees. To its left, the number of tens of tens, i.e. hundreds. To its left, the number of tens of hundreds, i.e. thousands, etc. Pepper still had more trees. Okay, that was a little myth. Understanding numeral systems. A numeral system is a way to represent numbers using symbols called numerals. Positional numeral systems. Introduce symbols and assign significance to the position of each digit. The number of numerals used defines the base of the system. So base 2, or sometimes called binary, we have two symbols, 0 and 1. Base 10, also called decimal, uses 10 symbols, 0 through 9, the Hindu-Arabic numeral system. Key terminology, we're going to look at this figure here. Number. A number is an abstract mathematical object represented by numerals. So over here on the bottom, the mathematical objects are numbers and then digits we'll get to in a moment. And then we have numeral as a symbol, the symbol used to represent a number. Each digit, or a symbol here, so those are the symbol numerals. And then numeral representation of a number using symbols, potentially multiple symbols. So a numeral as a representation can use multiple symbols. A numeral as a symbol is a single symbol numeral. Unfortunately, we use the same term for both of these. There's the numeral representation, which can include multiple numeral symbols. And unfortunately, that's just the terminology, so we're stuck with it. And then digit. The number represented by a single numeral or symbol is a digit. So this 8, for instance, is a numeral in the symbol sense, representing the number 8, which we would call the digit. Okay, that is the terminology around it. Interpreting numerals in different bases. We denote the base of the numeral system with a subscript, e.g. 1011, we have base 2 here, or 937, base 10. For subscripts, the base is 10. So the subscript itself, 2, 10, we're going to always use base 10 for that because we have to stop somewhere, right? It can't be just ambiguous bases all the way down. Here's an example. Base 10, decimal. The numeral 937 means 9 times 10 to the 2, so 9 hundreds. 3 times 10 to the 1, tens. 7 times 10 to the 0, 1. So 9 hundreds, 3 tens, 7 ones. Example in base 2 or binary, the numeral 1011 means 1 times 2 to the 3, or 1/8. 0 times 2 to the 2, which are 4s, so 0 4s. 1, 2 to the 1, so 1 2. And then 1, 2 to the 0s, which are 1s. So 1/8, 0 4s, 1 2s, 1 1. Ambiguity in numerals. Numerals like 1 1 can represent different numbers based on the base. So 1 1 in base 2 is 3 in base 10. 1 1 in base 10 is 1 0 1 1 in base 2. So if you just see the symbols 1 1 and you don't know which base it's in, it's hard to interpret. We often will assume it's in base 10 when we encounter a number because that's our most commonly used base. But in the context of computing, binary is very common, and so is hexadecimal, as we'll learn. Decimal numeral system. So it's an extension of the Hindu-Arabic system. used to represent both integers and non-integer numbers, utilizes a radix point, commonly the dot in a decimal, for non-integer representation. Place value in the decimal system. Digits to the left of the radix point are powers of 10, for example, 10 to the 0, 10 to the 1. Digits to the right of the radix point are fractions of powers of 10. So 10 to the negative 1, 10 to the negative 2, etc. So that's what the radix point denotes, is the separation between the powers of 10 and the fractions of powers of 10. Example, the decimal 2.73. 2 ones place, 7 in the tenths place, and 3 in the hundredths place. We're all very familiar with the decimal numeral system, but these concepts might be a little bit fuzzy or maybe never gone over before with you. So we go over them to help us understand how decimal works better, but also how binary and hexadecimal work as well. So hexadecimal numeral system. It's a base 16 numeral system. It extends the decimal system by adding 6 additional digits. So we have 0 through 9, so 10 digits, and then we add A, B, C, D, E, F. Those are the additional digits. Letters A through F represent values 10 through 15, right? So if we're counting up, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so for a total of 16, because 0 is in there as well, for a total of 16 different numerals, symbol numerals. Great. Convenience in computing. Widely used to represent the contents of computer memory due to its compactness. As we'll see, we'll be able to use 2 hexadecimal digits to represent an entire byte of memory. So it's very convenient. It works out, as we'll see. Each hexadecimal digit corresponds to 4 binary digits or bits, which we know as a nibble or half of a byte. Notation: hexadecimal numbers are typically prefixed with 0x, just so that you know which base is being used. Example, 0x9A780D38 is a hexadecimal number, and it corresponds to this in binary, 1001, etc., down to 1000. Now, you may notice that each of these binary nibbles can represent one of these digits. So 8, this is 8 in binary. And this is maybe a little bit easier to see. 3, 1 in base 10 corresponds to 1 in base 2. And then 2 in base 10 corresponds to 1, 0 in base 2. And then 3 in base 10 corresponds to 1, 1 in base 2. So you can always pad to the left with zeros to represent a number. So 0, 0, 1, 1 is 3. This corresponds to D. This is 0. So you see that these decimals, 8, 3, D, 0, are representing each of these nibbles of a binary number. Converting to and from decimal. Converting a base B number with digits xn, xn minus 1, down to x0, dot, so there's our radix point, x negative 1, negative 2, to x negative m, to decimal is straightforward. Represent each digit in base 10, and then use the formula x in base 10 is equal to the sum of xi, so the corresponding digit, b to the I. Okay, so for instance, here's an example. If we wanted to convert this binary number, which has a radix point in it, so a non-integer portion of the number, we can do that as follows. So 10.01, we have 1 times 2 to the 3, so the base is 2, base is 2. In this case, we have the 1 here corresponding to this 1 there. And then we have the 0 here corresponding to this 0 here. We have this 1, 1, 0, 0. And we've got descending powers of 2 here. And we've gotten down to 2 to the 0, which is just 1. Plus, and now we've got the fractional powers. So 0, the radix point, 0, and then 1. So we have 0, and then 1. And then the negative powers of 2. Negative 2 to the negative 1, 2 to the negative 2. So if you multiply all this out, add it together, we end up with 10.25. So we just converted this binary number with a radix point to a decimal number with a radix point. Sometimes we just call those decimal numbers, right? Similarly, if x16 is b8.f, so this is a hexadecimal number with a radix point, we can convert that to decimal by, again, using the same formula. So b here in our base 10 numeral system is 11. And it's in the 16 to the 1 place, so 16 to the 1 power, plus, so this is b. This is 8. 8 in hexadecimal is the same as 8 in decimal. So we have the 8, and it's in the zeros place, so 16 to the 0, plus f corresponds to 15, so it's the very last numeral in the hexadecimal system, and it represents 15. In base 10, we would write it 15 times 16 to the negative 1. So this is the fractional part. So if we multiply and add, we get 184.9375. So that is how to convert a binary number, a hexadecimal number, or a number of any base to decimal. Okay, converting from decimal. Converting from decimal to base B numeral system can be accomplished by the following procedure. Step 1. For the integer part of the number, successively divide by base B, represented in base 10. The remainder, xb, represented in base B of each step, is the base B digit in that position from right to left. It sounds a little complicated, but it's actually very simple. 2, for the fractional part of the number, successively multiply by base B10, the overflow x negative b of 1 base 10 and greater at each step is the corresponding base B digit in that position from left to right. So we'll do a simple example here in just a moment that will clarify what that means. Division and multiplication in this process are the usual base 10 versions. Technically, this process can be used for converting among other numeral systems, but it is not recommended due to our unfamiliarity with division and multiplication in these numeral systems. To convert between two non-decimal numeral systems, convert the original numeral into decimal, and then convert the decimal into the target numeral system. So generally, we've got our base 10 numeral system, our decimal, and we've got base 2 binary, we've got our base 16 hexadecimal, there's also base 8 octal as well. There are many, but if you ever want to convert from, say, base 2 to base 16 back and forth, what we often recommend is just going through base 10 in order to convert among these others. So let's look at a quick example here. Let's convert 1, 4 in base 10, so 14, our usual 14, to binary. The following table shows the division. So we start off with 14, and we're going to be dividing by our base, which is 2, repeatedly. So we divide 14 by 2, we get 7 with no remainder, so there's our 0. We divide 7 by 2, we get 3 with a remainder of 1. We divide 3 by 2, we get 1 with a remainder of 1. We divide 1 by 2, we get 0 with a remainder of 1. And this column of remainders becomes our binary number. 14 in base 10 is 1, 1, 1, 0 in base 2. So that conversion was from base 10 to base 2. In the previous slide, we covered how to go from base 2 to base 10 and any base to base 10. So we can go from base 10 to any of these other bases using this procedure. Converting between hex and binary. Binary numbers can be easily converted to hexadecimal and vice versa. There are 2 to the 4 equals 16 unique 4-digit binary numbers and 16 hex characters. This allows us to write each grouping of 4 binary digits, a nibble, as a single hex character, as we saw earlier, but it's good to kind of go over it again now that we know a little bit more. It is often easiest to convert each nibble to base 10 and then to hex. For instance, 1101 in base 2 is in decimal 1, so there's our 1, 1, 0, 1, multiplying by our base raised to the position power, gives us 13 in base 10. The 13th hex digit is D. So what we did here is we went from binary to decimal, so binary to decimal, and then we went from decimal to hex, which this was trivial because it was just a single digit, but we could have gone through the general procedure that we just covered. Similarly, one can convert a hex numeral to a nibble by converting it first to decimal and then to binary. So the reverse procedure works as well. Signed numeral systems and complements. Okay, so here's an introduction to the topic. In computing, it is convenient to encode the sign in the numeral representation. The method of complements provides an encoding of the sign that has the added benefit of computationally efficient arithmetic operation. A non-negative number n represented in base b with an integer part with n digits has b's complement, b to the n minus n for n greater than 0, and 0 for n equals 0. For instance, the base 10 numeral 25 has 10's complement, 10 squared, 10 raised to the 2 power, which is the number of digits used in 25. So 100 minus 25, which gives us 75. That is the 10's complement. Similarly, a number n in base 10 with only one digit has 10's complement, 10 minus n, or 0, as follows. So n is 0, 10's complement is 0. So that's this portion of the formula. And for the rest of the digits, we're going to use the 10 minus n formula. So 10 minus 1 gives us 9, 10 minus 2 gives us 8, etc., all the way to 10 minus 9 gives us 1. So here is the 10's complement for each of the single-digit decimal numbers. Okay, so it's reasonably straightforward to compute the b's complement, for b being the base. Signed numeral systems and complements, representing negative numbers. So now we're going to look at how to represent a negative number using the complement. As we can see, the complements are not themselves negative, right? They're just another positive number. Rather, they are used to represent negative numbers, okay? With our example of a single-digit decimal numeral, we can represent both positive and negative numbers as follows. So we're going to represent numbers -5 through +4 in this complement. So pure decimal 0 through 4 are going to represent positive integers 0 through 4, non-negative integers 0 through 4. And then we're going to use positive 5, 6, 7, 8, 9 to represent -5, -4, -3, -2, -1. And in this way, we can represent negative numbers with positive numbers. Each negative number is represented by the complement of its absolute value. So complement of absolute value of -4 is the complement of 4, which is 6. Complement of 3 is 7, etc. This results in the higher half of the single-digit decimal numerals representing negative numbers and the other half non-negative numbers. This numeral has a B's complement numeral system. Means its larger values represent negative numbers via the B's complement operation. Okay, arithmetic operations. How addition and subtraction work in a B's complement system? Let's take a look. Consider a number n in base 10, 10's complement numeral system that has only one digit. So again, we're sticking to those one-digit numbers. Add 2 to 2. So we could do that. We could find in the table, this table back here, 2, and then count rightward 2 places to get 4. So back to our table, we could start at 2, and we could count right 1, right 2, we get 4. Great. Add 2 to 4. Let's start from 4, and we would get 6 normally, which represents -4 by wrapping around. This is the wrong answer, so let's go back and look. If you count up from here, you would get, wrapping around, 5. So 4, 2, 5. And then 5 to 6. So 6, which represents -4. So this is not really what you get when you add 4 and 2, right? So it wraps around when we have this limited number of digits to represent the number. So this is something that happens a lot in computers. And this wrapping around is called an overflow. The same as carrying in basic arithmetic, when you add up to a point where something can no longer be represented with a single digit or the number of digits that you have to add another one to keep track. Subtract 3 from 2. So now let's move over to subtraction. So let's subtract 3 from 2. Try adding, so we could do our regular subtraction, but let's try instead adding the complement of 3 to 2. So the 10's complement of 3 is 7, right? So we can move rightward 7, which wraps back to 9, which represents -1. So let's look. We've got 2. So now I'm going to use a different color. So we're at 2, and we're going to wrap back. So we're going to add 7. So we're going to add the complement of 3, which is 7. So we're going to go 1, 2, 3, 4, 5, 6, 7. Okay, so that would give us 9. 9 corresponds in this 10's complement numeral system to -1. It represents -1, which is actually 2 minus 3, -1, as expected. So adding the complement worked for subtraction. So instead of subtracting in the usual way of moving leftward, we were able to move rightward by the complement and get back to the number that we needed. We can do this subtraction by adding the complement. This is actually a generally true procedure. For computers, it is actually more efficient to have a single operation, addition, that performs both addition and subtraction. So this is how computers will do a subtraction. They will use the complement of a number. Signed numerals and complements. Complement of a complement. So let's see what happens if we take the complement of a complement. For a non-zero number n, we have, from the formula for a complement, b to the n minus b to the n minus n, which these two terms subtract away. And we're left with a negative of negative n, which is positive n. So the complement is its own inverse. So the complement of a complement is the original number. This section has introduced the topic of modular arithmetic, arithmetic for which numbers wrap back, as we have seen in the case for those with a fixed number of digits for representation. So it's called modular arithmetic. We first encountered this with a modulo operator in chapter 0, and it will continue in our later discussion of encoder counting. We're going to come back to this in chapter 4. The examples in this section have been in base 10, but the concepts apply to any base. So you could do base 2, base 16, hexadecimal, etc. 2's complement numerals and the diminished complement. Consider a non-negative number n represented in base b with an integer part with n digits and a fractional part after the radix point with m digits. The diminished complement is the complement in base b minus 1, which is given by b to the n minus b to the negative m minus n. This is the b's complement minus b to the negative m. So the b's complement can be obtained from the diminished complement plus b to the minus m. This is useful to compute the b's complement because the diminished complement is easier to compute because b to the n minus b to the negative m is always the largest number that can be represented with a given radix point in n plus m digits. Let's look at an example. In base 10, with 2 digits left of the radix point, 1 digit right of the radix point, the diminished, or 9's complement, is 10 to the 2 minus 10 to the minus 1, so the 2 came from n, the negative 1 came from m, minus n equals 99.9 minus n. So for n equals 49.8, the 9's complement is 50.1. Notice that in the subtraction, so we just did a subtraction with 49.8. We subtracted 8 from 9, 9 from 9, and 4 from 9. In the subtraction, no borrowing was required because we always have the highest numeral in each place. So subtract each digit from 9. You can never get a digit that's larger than 9, so we're always going to have enough to not have to borrow. In the general case, subtract each digit from b minus 1. So this is the diminished complement. Computing this is easy because you never have to borrow when you're computing the diminished complement. Okay, so 2's complement using the diminished complement. For binary, the diminished complement is the 1's complement. This is simply 1 repeated n plus m times minus n. Just like for the 9's complement, it was 99.9. Here it's going to be 111.1 if there's a radix point. Example. The 1's complement of n equals 10100110 is given by 1111, 1111, all ones, minus n. So we compute that. Again, we'll never have to borrow. So 1 minus 0, 1. 1 minus 1, 0. 1 minus 1, 0. 1 minus 0, 1, etc. The effect of the 1's complement was the flipping of each bit. So each bit or digit for binary called bit is flipped. So the rightmost one was 0, now it's 1. The second rightmost was 1, now it's 0. etc. So each one got flipped. In a computer, such an operation is very simple to do. To get the 2's complement, we must simply add 2 to the negative m to the 1's complement. In the example, there is no fractional part, and often in our computations, there's no fractional part. They're integers. So we add 2 to the 0, which is 1. Okay, that is the 2's complement of 1, 0, 1, 0, 0, 1, 1, 0 is, so we flipped the bits here. So this was the diminished complement, the 1's complement. We flipped all the bits, and then we added 1. And so we add 1, so now we do have a carry. Sometimes that happens when we add 1. So 1 plus 1 is 0, carry 1. 1 plus 0 is 1. And then we continue to add 0 for the rest of the time, so it doesn't change anything after that. So we can compute the 2's complement by computing the 1's complement, which is just flipping all the bits, and then adding 1. So pretty easy to do, and computers like to do that. So 2's complement signed binary. A 2's complement signed binary integer with n digits represents not 0 through 2 to the n minus 1, as it would if it was unsigned, but rather negative 2 to the n minus 1 up to 0, and then up to 2 to the n minus 1 minus 1. In both unsigned and 2's complement signed binary, however, a total of 2 to the n numbers are represented by n bits. So either way, you represent the same number of numbers in those n bits. A table shows a 2's complement signed binary representation for n equal 4 bits, or a nibble. Note that negative numbers always have the leftmost bit 1. So in signed binary, we have 1, 0, 0, 0, 1, 0, 0, 1, etc., representing the negative numbers up to 0, and then we have our traditional unsigned counterparts for the positive numbers up to 7 for a nibble. A total of 16 values represented, and those 16 values, half of them are non-negative and half of them are negative. 2's complement, encoding and interpretation. The 2's complement operation can be performed by flipping all the bits and adding b to the negative m. Example, unsigned binary numeral 0010 1011 finds its signed binary equivalent. The process is as follows. So we're going to look for doing this process of 1's complement, which is flipping the bits, and then adding 1. So we flipped the bits, added 1. Now we're in the signed binary. Example, here's a second example. 2's complement signed binary numeral find its unsigned binary equivalent. The process is as follows. So we start with this signed binary, we do the 1's complement, we flip the bits, and we add 1. We get to unsigned binary. To go from unsigned to signed and from signed to unsigned, it's the same process because the complement is its own inverse. Okay. The general process of representing a number in signed binary and interpreting a signed binary are illustrated in the figures. So this upper figure is for a negative number. If you want to represent a negative number in signed binary, we take its absolute value. So say it was negative 3. Take its absolute value. This would give us positive 3. We represent it as unsigned binary. So now we would go, so 3 is 0, 0, 1, 1 in unsigned binary. We take its 2's complement to get to signed binary. So its 2's complement is going to be flip the bits and then add 1. So flipping the bits would give us 1, 1, 0, 0, and we would add 1 to that, and that would give us 1, 1, 0, 1. Okay, so this is the signed binary representation of -3. If we wanted to take that signed binary representation and convert it back to a decimal representation, we would take the 2's complement again. So we would flip the bits. So we would flip again. We'll go 0, 0, 1, 0. And then we would add 1 plus 0, 0, 0, 1 to get 0, 0, 1, 1, which is our unsigned binary representation. Look, it's the same as it was up here. Then we interpret it as a positive number. Okay, so we interpret it to be 3. Okay, and then we multiply 3 by -1 to get -3. -3 is the negative number that we encoded and then decoded. For a positive number, unsigned binary and signed binary are the same. Finally, signed hexadecimal numeral system. So to change the sign of a signed hexadecimal, take the 16's complement. It is easier to take the diminished 15's complement, then add 16 to the -m, where m is the number of fractional digits. So, example, convert 3a to -3a. The 15's complement of 3a is given by ff minus 3a. So again, the highest digit in the hexadecimal system is f. So ff minus, we're never going to have to borrow here, minus, so f minus a is 15 minus 10, which is 5. 15 minus 10 is 5. And we have 15 minus 3 is 12, which is 12, which corresponds to C. 10 is A, 11 is B, 12 is C. So C5. So that's the 15's complement. To obtain the 16's complement, we must simply add 16 to the 0, which is 1, to the 15's complement. So C5 plus 1 is C6. Therefore, the 16's complement of 3a is C6. To check, we see that in unsigned hexadecimal, if you add C6 and 3a together, we're going to get 0 carry, and 1. So 100. We overflowed by 1. This implies that in unsigned hexadecimal, C6 and 3a together overflow the representation in 2 hexadecimal numerals, requiring the lowest 3-numeral hexadecimal numeral. This overflow always occurs with the unsigned sum of the 2's complement, or the, in this case, the 16's complement, the b's complement. With an understanding of several important representations of numbers that we've gained throughout this section, we can now proceed to a study of their representation in computer memory, which has been motivating us so far to look at numeral representations. So, all right, I'll see you next time to talk about memory.